So I think in the last lecture we have discussed what is mean by eigenvectors, how to find the eigenvalues and everything. Is it okay?
Yes, sir.
Yes or no? So let's check it out. And I have given some example as a homework also. This is what the example I have given for the homework. Find the eigenvalues and eigenvector of a given square matrices. Okay. So this is what we have. So anyone done that? All the examples? Yes or no? Okay, just do that such kind of examples. Huh? And I think this is what the example I have given you for the tutorial also. Okay. Okay. So in today's lecture, we are going to see one theorem. I think some of you already know this theorem. And we are going to solve the examples on it. The theorem is called as Cayley-Hamilton theorem. So write down everyone. So what the theorem says, what's the statement of the theorem? So the Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. That's it. That is what we have the theorem. Now tell me, what is meant by characteristic equation? What is characteristic equation? Anyone? What is characteristic equation here? Am I audible clearly? Yes or no?
Sir,
Okay.
equation A minus lambda equal to
Okay. Okay. So let's revise the thing first. So when we have determinant of matrix A is nothing but the square matrix minus lambda into I is equal to 0. That equation is called as your characteristics equation. Yes or no? So you put the values of A, you put the I is nothing but the corresponding identity matrix, and you find out that determinant whatever you are getting, that is nothing but the characteristic equation. So what Cayley-Hamilton says, that Cayley is the one scientist and Hamilton is the another scientist. They stated the theorem. What they are saying, you can take any square matrix, you can take any square matrix, that square matrix satisfies its own characteristic equation. It means what? This is what I have the characteristic equation. If I find the characteristic equation and if I substitute instead of lambda A, then that equation is satisfied. For example, let's take a 2 by 2 example. A is nothing but suppose my matrix. I'm taking any matrix, so I just take 1, 2, 3, 4. So 1, 2, 3, 4. Can you find characteristic polynomial for that particular equation? How one can find the characteristic polynomial? This implies for 2 by 2 matrix, or how to find the characteristic polynomial. Yes, anyone?
sir, first finding values of lambda.
So how one can find the values of lambda?
Sir, simply
A
sir
minus
values
lambda.
characteristic में equation value put.
Yeah, so what you substitute here values. Okay, that characteristic equation. So determinant A matrix. So A matrix is 1. Lambda is I. Here I is nothing but 2 by 2 identity matrix. So diagonal we have only lambda lambda. So I can write down 1 minus lambda. Here 2 as it is. Here 4 as it is. Here 3 minus lambda. And I find that determinant which is equal to be 0. So if I try to find it, 1 minus lambda into 3 minus lambda minus 8, which is equal to 0. If you solve this, what you are getting? Tell me now. Lambda square, yes, minus 4 lambda plus 3 minus 8, which is equal to 0. Yes or no?
Yes,
Check it
sir.
out. Okay.
Yes, sir.
So once you solve this, you are getting minus 5. So lambda square minus 4 lambda minus 5. Here nothing is there. It means we have I there, which is equal to 0. Or you can forget I. When I substitute the values, that time you will understand. Okay. So this is I have for the characteristic polynomial. This is I have my characteristic polynomial or equation. Okay. So now once we have this equation, what theorem says that? What is our theorem? That theorem says that every square matrix, so that A square matrix, that A satisfy its own characteristic equation. This is what I have my characteristic equation. So what the theorem says that if you substitute the value of A in that equation, then also that equation is satisfied. So what Cayley-Hamilton theorem says that? So by Cayley theorem or Cayley-Hamilton theorem, by Cayley-Hamilton theorem, what they are saying, instead of lambda, if I substitute A, so A square minus 4A minus only 5, instead of writing 5, I write down identity also, because I'm substituting now matrices. So I is nothing but the identity matrix, which is equal to 0. So let's verify this, whether this is true or not. Okay. So first, what is our A matrix? My A matrix is 1, 2, 4, 3. Okay. What is my A square? Can someone tell me what is my A square here? Can someone find what is A square? So if I multiply, so 1 and 8, it becomes 9. So here 2 and 12, it becomes, if I multiply first row and second column, so 1 into 1 and 2 into 4, 7 plus 1, 8. Am I correct? Then I'm getting 8 here. Here I'm getting 16. Here I'm getting 17. Check it out whether this is correct or not. A into A. I can find here. 1, 2, 3, 4. And again 1, 2, 3, 4. So 1 into 1.
Yes,
4 to
sir.
the 8 plus 9. That is correct.
Yes, sir.
So first or second column, 3 to the 6, 6 plus 1, 6 plus 2 is 8.
Sorry,
4 plus 12, 16, and 8 plus 9, 17. So this is what you have A square. Now substitute find LHS and RHS here by Cayley-Hamilton theorem. So what is our LHS? So left hand side I have A square minus 4 into A minus 5 into identity matrix. Okay, so what is my A square here? A square, I have this matrix, so I just substitute this value. So 9, 8, 16, 17 minus 4 into my A matrix. A matrix is 1, 2, 4, 3 minus 5 into identity matrix 1, 0, 0, 1. Now just solve this. What you are getting, check it out. This remains as it is. 16, 17. You multiply inside, so it becomes what it becomes? 4, 8, 16, and 4 these are 12, no? well, minus, it becomes 5, 0, 0, 5. And if you solve this further, 9, 8, 16, 17. So we have subtraction here. So minus, what I'm getting here? 5, this minus 4, minus 5, what I'm getting? Minus 9. So I take minus outside, so it becomes 9. So here 8 minus 8 minus 0. So I'm getting minus 8. So I just take minus outside. Here I'm getting 8. Here I'm getting 16 and here I'm getting 17. So what you are getting?
Zero matrix.
Yes, that is nothing but your RHS. That 0 stands for zero matrix. Clear and clear?
Yes, sir.
Okay. So what is the use of that now? Okay. So this is the very big invention at that particular time, because you observe that. So you can take any square matrix. Here I just consider a 2 by 2 matrix, but it is true for any square matrix. It may have order 10 cross 10. It may have order 20 cross 20. It is a square matrix. Find its characteristic polynomial, and once you got the characteristic polynomial, that characteristics polynomial satisfied by the matrix itself. Okay, so what is the use of that? So here we are going to use that particular theorem to find the inverse of a matrix. Okay, but inverse is not always exist. So we are going to see also how the inverse we can find. Okay, if it is exist. Okay, so let's take the same example. Just write down with this thing. Everyone done with that?
Yes, sir.
Anyone any doubts
Yes,
here
sir. No, sir.
of the Cayley-Hamilton theorem? It's very easy. Just keep the statement in your mind that every square matrix satisfies its own characteristic polynomial. So this is first find the characteristic polynomial and directly substitute. Instead of lambda, you can substitute the value A. Okay, matrix A. Okay, so this is what we have an example. Now suppose in that particular example, find the inverse of A by using Cayley-Hamilton theorem. If we may ask you, okay, find the inverse of A by using Cayley-Hamilton theorem. So what you are going to do, first find out characteristic equation, and by Cayley-Hamilton theorem you have this equation. Okay, this equation is satisfied. No need to check now every time. So the star equation is satisfied. So we have star. So from star, what I have equation A square minus 5, 4A minus 5, 4A. A square minus 4A minus 5I, which is equal to 0. Now you wanted to find A inverse, no? So multiply if it is exist. So check it out whether determinant is 0 or not. So find out the determinant of E. So what I have A? I have A is nothing but 1, 2, 4, 3. So what is this determinant? So 3 minus 8. What it is? Minus 5. Okay, which is not equal to 0. Means inverse is exist. Okay. So once the inverse exits, what you need to do? Multiply A inverse on the both sides. Okay. If you multiply by A inverse, what you are getting? A inverse into A square minus 4 into A inverse into A minus 5 into A inverse into identity, which is equal to 0 into anything is 0. Now tell me, what is the value of this? A inverse into A square.
Sir, A.
It is A only. Very good. Minus. What is the value of A inverse into A?
Sir, minus 4.
Minus 4 into identity matrix. Okay.
Yeah.
And here what are you have only 5 into A inverse, which is equal to 0, because identity matrix into any matrix is nothing but your that matrix itself. What you need to find out? You need to find out the value of A inverse. So shift that A inverse to another side. So what you are getting A inverse is equal to 1 divided by 5 into, I just shifted this term here, so it becomes plus, so that remains as it is. A minus 4 into identity matrix. That's it. You can find now. Substitute the value of A and I. So what you are getting 1/5, that number as it is. You have A matrix. So A matrix is nothing but here 1, 2, 4, 3. So I just make a big bracket because it is multiply to everything. And 4 into identity matrix is nothing but 4, 0, 0, 4. And once you calculate this 1/5, you are getting 1 minus 4, you are getting -3. Yes or no? 2 minus 0, you are getting 2. 4 minus 0, you are getting 4 itself. And 3 minus 4, you are getting -1. And multiply that 5 inside, or you can keep as it is, no problem. This is what you have A inverse of a given matrix. Clean and clear?
Yes, sir.
Okay. Now, whether you have any question here, or I will ask you question.
So ये determinant non-zero क्यों होना चाहिए?
Yes, exactly. That is what I am expecting this. Because for finding inverse, this is the basic requirement. To finding inverse, if determinant, yes, hello. Yes. Okay. For finding inverse, I am not getting what?
Guys, sir है क्या ग्रुप अभी मीटिंग में?
आवाज नहीं आ रहा है आपको? Yes, please.
सर हमको आ रहा है.
Tanmay Panda. Yeah, you are asking something, no? Roll number 56. Is it okay? Am I audible clearly?
Hello, sir.
Yes.
हाँ सर, वो ट्यूटोरियल का क्वेश्चंस आप डिस्कस करने वाले?
यहाँ पे नहीं, यहाँ पे बात है.
अच्छा, ओके सर.
Okay. So what happened where we are? Yeah. So for finding the inverse of particular any square matrix, you should have determinant is not equal to 0. Then and then only inverse is possible. But someone is saying, sir, we are not using anything here. Even if my determinant is equal to 0, can we find the inverse by using this method? So that is what my question. What problem you faced? If I have a matrix which has determinant 0, and if I apply this method to find its inverse, what happened? Whether I will get the inverse or not? That is what I have a question.
No.
Why? Let's check it out. Let's take an example, then a simple example whose determinant is equal to 0. Find its characteristic equation and try to find its inverse. Okay, so you will understand. But here, if you check this thing, it's okay. If you just consider it is non-zero and you can find it, it is also okay, no problem. But for finding inverse, you should have determinant should be not equal to 0. If it is 0, by using this method, you cannot find the inverse. You will face a difficulty. What kind of difficulties? You will never get that A inverse like that. Let's see. Let's see. Suppose I consider an example, a simple example, 1, 2, 1, 2. So determinant is equal to 0. You can easily check it out. Yes or no?
Yes, sir.
So what is this characteristic polynomial becomes? So 1 minus lambda, here 2, here 1, and here 2 minus lambda, which is equal to 0. So what you are getting? 1 minus lambda, 2 minus lambda, minus 2, which is equal to 0. So you are getting lambda square minus 2 lambda, 3 lambda, which is equal to 0. Yes or no? Check it out. This if I multiply here, so you are getting plus 2. That plus 2 minus 2 get cancelled. This multiply here minus lambda, minus 2 lambda, that is minus 3 lambda, minus plus lambda square. That is what you are getting characteristic equation. Yes or no?
Yes, sir. Yes, sir.
Okay. So by using Cayley theorem, what you are getting? A square minus 3a, which is equal to 0. Okay. And suppose here determinant is equal to 0. Determinant of A is equal to 0. So we know inverse does not exist. But even if I try to find, even if I try to find, I assume that A inverses exist. So assume that A inverses exist. Then what happened? If I multiply by A inverse, so A inverse into A square minus 3 into A inverse into A, which is equal to 0. So what you are getting? What is A inverse into A?
A.
You are getting A minus 3
3 into
into
identity.
identity
ID.
matrix, which is equal to 0, where you are getting A inverse.
Yes, sir.
Okay,
Yes,
so that is what you are not getting. When you are not getting identity matrix, it means what? You will not able to find the A inverse. See, now one more. This is for 2 by 2. What happened for the 3 by 3? So A inverse does not exist. Okay. Okay. Now, everyone understand that? Please write down this. Please write down this. Okay. So what happened for the 3 by 3 matrices? See. So write down the remark. For any 3 cross 3 matrix, we have characteristic polynomial yes. What is that characteristic polynomial? First one, lambda cube minus yes
S2
s1
lambda S1 sorry S1
s1
lambda
lambda
square
square
plus
plus
S2 lambda
s2 lambda minus
minus
determinant
determinant
of
of
power,
A.
which is equal to 0. Where what is s1?
Sum of the main diagonal elements.
So we call that trace of it. Very good.
Yes.
What is s2?
Product of the minors.
Sum
Sum
of
of
diagonal
sorry.
minors. And determinant of A you can calculate. See, even if I have determinant of A is equal to 0 here, okay, for suppose for any 3 by 3 matrices, so this will directly become 0, so you are not getting identity matrix, and again you are not able to find the inverse. Okay, so let's take one example on this. Yeah, by using Cayley-Hamilton theorem, find inverse by using Cayley-Hamilton theorem. Example. Cayley-Hamilton theorem. T-O-N only, not E. Find inverse of E. What they have given A, 2 minus 1, 1, 3 minus 2, 1, 0, 0, 1. Okay. So when they are saying Cayley-Hamilton theorem, it means you need to use the Cayley-Hamilton theorem only. So find out its equation and everything.
सर
Yes.
एक डाउट था,
Yes,
लाइक
please.
3x3 मैट्रिक्स में तो इस फॉर्मेट में लिख दिए लैम्डा क्यूब माइनस S1 लैम्डा स्क्वायर प्लस S2 लैम्डा इस टाइप से, लाइक
Okay.
जैसे हायर ऑर्डर पे जाती है तो इसलिए ये जनरलाइज फॉर्म है या फिर उसको नॉर्मल
नहीं
वैसे सॉल्व
नहीं,
करना
it's
पड़ता है?
it's for 3 by 3 only. When you goes for the 4 by 4, we have lambda raised to 4. So that time formula may different. This is for only 3 by 3, up to 3 by 3. You can find out this for 2 by 2 also. What happened for 2 by 2? See here, let's take an example. We have characteristic polynomial and everything here for this matrix. See, so for 2 by 2 matrix, what happened? The same formula will work. It becomes lambda square minus S1 lambda. Okay, so what is S1? S1 is nothing but your trace, and plus determinant of A, which is equal to 0. Alternate plus or minus sign. So this formula will work. See, lambda square, you are getting lambda square. Trace is nothing but addition of that. So 4. If I substitute S1 is equal to 4, so 4 lambda, and determinant of 3 minus 8 minus 5. So I am getting minus 2. So this formula will work only for up to 3 by 3. For 4 by 4, we have 4 coefficient, lambda raised to 4, lambda cube. So for that purpose, we may have a different formula. Okay, so here S2 is not in the picture. So when we go for the higher order, S2 comes in the picture. Again, if I go for the higher order, some S3 comes in the picture. Okay, like that. Got it?
Yes, sir.
So this is for only 3 by 3, up to 3 by 3. This form. So that's why every time I have mentioned here for any 3 by 3 matrix. Okay, tell me, what is S1 here?
1.
1. Okay. What is the value of S2? So let's calculate S2. So first determinant diagonal trace, sum of the
-1.
diagonal minor. So it becomes, okay, you can directly tell me now. No need to write down the values and thing. So it becomes -2. Very good. Plus, so this get cancelled, this get cancelled. Again, I am getting 2. Yes or no? And plus this -4 plus 3. What is -4 plus 3? So it becomes -1. Yes or no?
Yes, sir.
Okay. And what about determinant of A? Determinant of A.
Sir, -4.
-4. Check it out.
-1.
-1. I think it should come something like that. -1.
Sir, -1.
-1, no? So what
Yes,
is my
sir.
characteristic polynomial? So my characteristic polynomial becomes lambda cube S1. S1 is nothing but 1. So minus lambda square. S2 is nothing but the -1. So again minus lambda only. And this become plus 1, which is equal to 0. Check it out whether this is everyone getting or not.
Yes, sir.
Okay. So once you got this, so by using Cayley-Hamilton theorem, here sometimes we may ask you verify Cayley-Hamilton theorem and find A inverse. That time you need to find a cube, a square, a like that only. But sometimes we directly ask using Cayley-Hamilton theorem find A inverse. So verify means what? You need to substitute the value of A also. Okay, and you need to find out a cube, a square, and everything, and then you need to get the answer. So characteristic polynomial. So by Cayley-Hamilton theorem. So for Cayley-Hamilton theorem, what I'm getting a cube minus a square minus A minus identity matrix which is equal to 0. So here we have determinant of A which is not equal to 0. We already calculated here. It means A inverse is exist. So multiply A inverse. So
वो लास्ट में प्लस आइडेंटिटी मैट्रिक्स आएगा ना
प्लस क्यों आ जाएगा? ओके सो माइनस प्लस है ना यहाँ ओके यहाँ करें यहाँ पे प्लस भी है ना नाउ इट इज ओके लैम्डा क्यूब माइनस लैम्डा स्क्वायर हाँ इट्स ओके नाउ multiply A inverse so what I am getting A inverse into A cube minus A inverse into A square minus A inverse into A plus A inverse into identity which is equal to 0. What I am getting here, tell me?
A square.
A square minus here
A.
E minus here
Identity matrix.
identity matrix and here only A
A
inverse
inverse.
which is equal to 0. So this implies I need to find the A inverse. So A inverse is equal to I shift everything to that side. So if I shift, so I am getting first identity matrix plus sign plus A matrix minus A square. Now find out A square and substitute here, you will get A inverse. Then what is the value of A inverse? So A inverse is equal to identity matrix plus A. So I can directly write down what is my A matrix. If I add the identity matrix, so I'm getting 3 minus 1, 1 as a diagonal. So what I'm getting here, identity matrix plus A, I can directly write down. Huh? You just solve it. I'm getting here 3, here minus 1, here 1 as it is. Here 3, here minus 1, and here 1 as it is. Then 0, 0. I'm going to add 1 plus 1, so I'm getting 2 here. Yes or no? Minus A square. What is A square now then? What is A square?
Sir,
Yes.
102.
102. Then
012.
012. Very good.
001.
001. Now subtract that thing. You will get your A inverse as A inverse is equal to. If you do the subtraction, I am getting 2 minus 1 minus 1. Then 3 minus 0, 3, 1 minus 1, I am getting 0 here. Again 1 minus 2, I am getting minus 1. And here simply 0, 0, 2 minus 1 is 1. That is what you have your A inverse. This is what we have for the Cayley-Hamilton theorem and its examples. We don't have division algorithm here. By using division algorithm, you can find a power of any power of the matrix. If you're done with that, tell me, I will give you one more example. Done with that?
Yes, sir.
Okay. So one MCQ example for you peoples. So what we have MCQ, if a matrix A is equal to, give me a minute, I will check it out. What I should get. Okay, just give me a minute. I will try to construct the example. So I want here this matrix. Here something square. Yeah. Okay. If my A is equal to 1010, then find A raised to 1000. Tell me, what is the value of A raised to 1000? We may ask you sometimes 3 by 3 matrix. The procedure is same. Whether it is feasible to everyone?
Yes, sir.
Yes, sir.
Tell me, what is A raised to 1000?
So we have to do this as
Do it. Calculation, do it, and then tell me directly the answer. Then I will explain. I just want answer from your side. It is just a MCQ kind of question. If I have 2 by 2 matrix, so it requires 1 or 2 minutes. Try to solve.
So would it be the identity only?
Yes, that's a correct one. It's an identity matrix. How you solve this? Yes.
So finding
First, it is square matrix, so it satisfies
the
characteristic.
characteristic equation and
So I find its characteristic equation. So 1 minus lambda, here 0, here 0, here I am getting lambda, or 0 minus lambda, something like that, no? Okay. So which is equal to 0. So what this implies? 1 minus lambda into minus lambda, which is equal to 0. If I multiply, yes or no? Check it out.
yes, sir.
Okay, and once you multiply this, what you are getting? Minus lambda plus lambda square, which is equal to 0. If I multiply here, so it becomes minus lambda plus lambda. What I want? So it satisfies its own characteristic equation. So I'm getting lambda square minus lambda, which is equal to 0. This is what I am getting my characteristic polynomial. So substitute value of A here. So what I am getting? A square is equal to A itself. Yes or no?
Yes, sir.
If I take again square on both sides, if I multiply by A square, what I'm getting? A raised to 4 is equal to A square. Yes or no?
Yes, sir. Yes,
So
sir.
what is A square?
A.
Equals to A.
So what I'm getting? A raised to 4 is equal to A. If I again multiply by 4, what happened? So how you can proceed that? Tell me now. If you take directly from here equation, if I take A raised to 500, so A square raised to 500, which is equal to A raised to 500. So it is A raised to 1000. So how you can find out this? Okay, tell me what is A raised to 3? You can write down A raised to 3, A square into A. Yes or no? Again,
Yes, sir.
what is A
Yes, sir.
square? Again, A into A.
A.
What is A into A? A square, that is nothing but A.
A.
What is A raised to 4? You can write down A square into A square. What is A square? A square is nothing but A. You are getting A into A, which is nothing but A square again. So I am getting A here. What is A raised to 5? A raised to 4 into A. What is A raised to 4 you calculated? Which is A into A, you are getting. What can you say about A raised to 1000?
It will be also equal to A.
Yeah, that is what I'm saying. So that is what the correct answer. A. So this is what some kind of tricky question we may ask. Okay. Got it, everyone?
Yes, sir.
Okay, so write down that. So we may give you an option. Okay, we may give you an option. So you need to find out the correct answer from the options. For 3 by 3 also this will happen, sir. For 3 by 3 also you will get the same thing. Okay, so that's what we have for the eigenvalues, eigenvector, and Cayley-Hamilton theorem. Okay, anyone any doubts up to this? Any doubts, anyone?
No, sir.
No, sir.
Okay, so we have 15 minutes remaining. So in the next lecture, what we are going to do, in the next lecture, we are going to see what is mean by orthogonal matrix. So I'm just going to give you a definition. I'm just going to give you a definition. You need to think on that definition. And in next lecture, we are going to solve this examples on that particular theme. So orthogonal matrix. So write down.
So
Yes.
अभी ये यूनिट खत्म ना मतलब
Yes. Yes. Yes.
मैट्रिसेस अभी खत्म ना
Matrices is done here.
अभी नेक्स्ट क्या कराने वाले हैं?
Applications of the matrices and orthogonal matrix.
और उसके बाद
we have nth derivative.
अच्छा मतलब कैलकुलस स्टार्ट कर देंगे.
Calculus, yes.
ठीक है.
Okay. So what is orthogonal matrix? Matrix is said to be orthogonal. A matrix A is said to be orthogonal if A into A transpose is equal to identity, or A transpose is equal to its inverse. The both definitions are equivalent. If you multiply by A inverse on both sides, so A inverse and A, it becomes identity, and identity to A inverse, it becomes A inverse. So A transpose is equal to A inverse. Okay.
Yes, sir.
So that time, that matrix is called as a orthogonal matrix. If you take, what is A transpose? What is A transpose? Anyone? A transpose?
The matrix obtained by changing the rows and columns.
Correct. The matrix is obtained by interchanging its rows and columns. Correct one. So I'll just give you one example. You check it out whether it is orthogonal or not. 2 by 2 matrix. So it's very easy. So minus 1, 0, 0, 1. Check it out whether it is orthogonal or not. What is A transpose? Tell me here. What is A transpose here? Am I audible clearly?
Yes, sir. Yes.
What
Yes,
is
sir.
A transpose? For
Minus
A?
1, 0, 0, 1.
minus
Same
1,
one.
same matrix. Yes,
Same
exactly, same matrix. So now find, so A into A transpose. So I just
Yes,
find
sir,
out.
it is
It comes,
orthogonal.
no, it comes identity matrix.
Yes, sir.
So it is orthogonal. So I calculated this. So minus 1, it becomes plus 1. Again, it minus 1, it becomes 0, it becomes 1. No, first row, second column. So it becomes 0, it becomes 0. So second, this becomes 0, this becomes 0. Second row, first column, second row, second column, 0, 0, 1. So we are getting identity matrix. So it is orthogonal. Okay. Now, homework. Check whether it is orthogonal or not. A is equal to cos theta sin theta minus sin theta into cos theta. This is what we call as the rotation matrix. While giving the examples, that time I will homework example. A is orthogonal. Yes. Find its inverse. What? And also I want one example from your side of 3 by 3 matrix which is orthogonal. You can find any example. Any example of 3 cross 3 which is orthogonal. Yes, any doubts?
सर
Yes.
लाइक जो कंडीशंस दी आपने ऑर्थोगोनल के लिए वो दोनों सेटिस्फाई होनी चाहिए ना,
और है ना, और
कोई एक हो तो भी चल जाएगा.
हाँ एग्जैक्टली क्या किया है देखो यहाँ पे, अगर इफ आई मल्टीप्लाई बाय a इनवर्स आई एम गेटिंग दिस कंडीशन, so these two equation, that two conditions are equivalent.
Oh sir, yes sir.
Okay, so once it is orthogonal, it means this is also satisfied. Okay, so just check for this condition only. Okay, and also I want 3 by 3, any 3 by 3 matrix which is orthogonal, any 3 by 3 matrix. Okay. So we will stop here then.